Tonight, we're going to answer a question that sounds deceptively simple, but turns out to be one of the most sobering calculations in all of science. How far can humanity actually travel? Not in theory, not with warp drives or wormholes or any of the physics-defying technologies that science fiction has been promising us for a century. With what we have, with what we can realistically build, with what our bodies can actually survive. Because there is a number, there is a real, measurable, physically constrained boundary beyond which space stops being a destination and starts being a sentence. And by the end of tonight, you're going to understand exactly where that boundary is, why it exists, what forces are conspiring to keep us locked inside it, and why the universe is far less interested in our survival than we tend to assume. This isn't a conversation about pessimism, it's a conversation about honesty, because the gap between what we think we can do and what physics actually allows is enormous. And understanding that gap, truly grasping it, changes how you think about everything from Mars colonization, to the search for extraterrestrial intelligence, to the long-term future of our species. The universe has rules. Those rules do not negotiate. And the question of how far humanity can travel before those rules become insurmountable walls is one of the most important questions we can ask right now. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with where we actually are. Right now, in April of 2026, humanity's reach beyond the surface of Earth is honestly embarrassing compared to what most people imagine. The International Space Station orbits at an altitude of roughly 260 miles above Earth's surface. That sounds like a long way up. But if you drove a car straight up at highway speed, you'd be there in about 4 hours. The ISS is not in deep space. It's not even in space in the way most people picture it. It's essentially skimming the top of the atmosphere, held up by the constant free fall of orbital mechanics, operating inside Earth's magnetic field, protected from the worst of the radiation environment beyond. For 56 years, the farthest humans had ever traveled from Earth was 248,655 miles. That record belonged to the crew of Apollo 13 in 1970, who swung round the far side of the moon on a trajectory forced on them by an equipment failure that nearly killed them. They set that record not through triumph but through disaster. Then on April 6, 2026, NASA astronauts Reid Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen, quietly erased it. The Artemis II mission pushed to a maximum distance of roughly 252,760 miles from Earth, surpassing Apollo 13's mark by more than 4,000 miles. The Moon itself averages about 239,000 miles from Earth, a distance so modest that light covers it in about 1.3 seconds. On cosmic scales, this is nothing. This is the equivalent of stepping out your front door and calling it a road trip. And yet breaking that record took us 56 years. Since the Apollo program ended in 1972, no human being has traveled more than about 400 miles from Earth's surface. More than 50 years have passed. We went to the Moon and then we stopped. We retreated to low Earth orbit and stayed there. Not because we got bored, but because actually going farther turned out to be harder than we thought. The physics kept getting worse the farther out we tried to reach. The unmanned spacecraft we've sent out, a much more impressive Voyager 1, launched in 1977, is currently approximately 15 billion miles from the Sun. It crossed the heliopause, the boundary of the Sun's magnetic influence, in 2012 and entered interstellar space. It is the most distant human-made object in existence, but even Voyager 1, our most ambitious physical reach into the cosmos, is still in our cosmic neighborhood. The nearest star system, Alpha Centauri, is about 25 trillion miles away. Voyager would take roughly 73,000 years to reach it at its current speed, and it isn't even heading in that direction. So that's the baseline. Humans have reached the Moon, about 250,000 miles out. Robots have reached the heliopause, about 15 billion miles out. And the nearest star is about 25 trillion miles away. The scale here matters. Let me put it in terms that actually land. If the distance from Earth to the Moon were 1 inch, the distance to the nearest star would be almost 27 miles. We've gone 1 inch and are debating whether we can reach 3 inches. The nearest star is 27 miles away by this scale. Now, with that baseline established, let's ask the real question. What are the actual barriers? What forces, physical and biological, are fighting against us every time we try to go farther? Because there isn't just one barrier. There are several, and they stack on top of each other in a way that gets genuinely ugly very quickly. The first barrier is fuel and the rocket equation, which is one of the most tyrannical relationships in all of engineering. It was derived by Konstantin Tsiolkovsky in 1897, and it has been humbling rocket scientists ever since. The basic problem is this: to go faster, you need more fuel, but fuel has mass, and accelerating that mass requires more fuel, and that additional fuel has mass, and accelerating that requires more fuel, and on in an exponential spiral that makes deep space travel with chemical rockets essentially absurd. Consider the numbers. The Saturn V rocket that took the Apollo astronauts to the moon stood 363 feet tall and weighed about 6.2 million pounds at launch. Of that total weight, the actual payload delivered to the moon, the 3 astronauts and their equipment, was roughly 100,000 pounds. The rest was fuel and rocket stages that got burned and dropped along the way. You needed roughly 60 pounds of rocket to deliver 1 pound of astronaut to the lunar surface. And the moon is 1 inch away by our earlier scale. For Mars, which is on average about 140 million miles from Earth, the fuel requirements become staggering. A Mars mission using conventional chemical propulsion requires spacecraft masses in low Earth orbit of several hundred tons before the journey even begins. SpaceX's Starship, the most capable launch vehicle being developed today, is designed to address some of this through reusability and in-space refueling. But even Starship represents an incremental improvement within the domain of chemical propulsion. You're still fundamentally burning hydrogen and oxygen, or methane and oxygen, and exhausting them out the back. And here's what really matters. The rocket equation doesn't scale kindly. Going to Mars takes perhaps 10 times more fuel than going to the moon. Going to Jupiter takes exponentially more than going to Mars. By the time you start thinking seriously about reaching the outer planets with human crews, the fuel requirements have spiraled into a regime where conventional chemical propulsion isn't just difficult, it's categorically inadequate. You cannot brute force your way through the solar system with a bigger tank of kerosene. The physics won't allow it. This is why nuclear propulsion has been discussed seriously for decades. Nuclear thermal propulsion, where a nuclear reactor heats a propellant like hydrogen to very high temperatures and expels it for thrust, can achieve roughly twice the efficiency of the best chemical rockets. That's a real improvement. It could cut travel times to Mars significantly. But twice the efficiency of something that's fundamentally inadequate doesn't make it adequate. Nuclear thermal propulsion would help get us to Mars faster. It would not get us to Alpha Centauri. For genuinely reaching the outer planets with human crews, you'd need nuclear electric propulsion or some form of fusion drive. Technologies that either work only at very low thrust levels or that we haven't actually built yet. The ion drives we've used on unmanned spacecraft are real and functional, but they're extraordinarily gentle. The Dawn spacecraft, which orbited Vesta and Ceres in the asteroid belt, used ion propulsion beautifully, but its acceleration was measured in fractions of a millimeter per second. If you turned off gravity, you'd get a better sense of the push from breathing on a piece of paper. Ion drives are patient and efficient, perfect for unmanned missions with years to build up speed. They are not how you get a crew of 6 to Jupiter's moons before their life support runs out. So barrier 1 is propulsion. We do not have the technology to move large masses of people and equipment through the solar system in reasonable time frames. And the outer solar system is essentially off the table with anything resembling current technology. But let's say we solve propulsion. Let's imagine fusion reactors become small and efficient enough to build spacecraft drives. Let's imagine we achieve sustained plasma jets with specific impulse that makes the rocket equation tractable. What's barrier number 2? Radiation. And this one is deeply personal because it attacks the very biology of the people doing the traveling. Here on Earth, we are extraordinarily well protected from the radiation environment of space. Earth's magnetic field deflects most of the charged particles streaming from the sun and from distant cosmic sources. Earth's atmosphere provides shielding equivalent to roughly 10 meters of water. Together, these two shields bring our radiation exposure down to a background level of about 0.3 rem per year from natural sources. You live inside a radiation shelter and you've never had to think about it. Leave that shelter and the numbers change dramatically. Aboard the International Space Station, which orbits within Earth's magnetic field and receives some protection from Earth's bulk blocking radiation from below, Astronauts receive roughly 15 to 20 REM per year. That's 50 to 60 times the surface dose. 6 months on the ISS, which is a typical mission duration, exposes an astronaut to about 8 to 10 REM. This is considered acceptable risk. It slightly elevates lifetime cancer probability, but not catastrophically so. Now step outside the Earth's magnetic field. Now you're in deep space. The sun's solar wind and cosmic rays from the galaxy stream through you with nothing to stop them, except whatever spacecraft wall happens to be between you and the void. On a journey to Mars taking 6 to 9 months, a crew would receive roughly 30 to 40 REM from galactic cosmic rays alone, and that assumes no major solar particle events. Solar flares and coronal mass ejections can deliver hundreds of REM in a matter of hours. During the Apollo missions, which lasted less than 2 weeks and mostly occurred during solar minimum, the astronauts got somewhat lucky. A large solar particle event during Apollo would have been potentially lethal. For a Mars mission, NASA's current career radiation limits for astronauts, which vary by age and sex, but cap lifetime exposure at 100 to 200 REM, depending on cancer risk factors, would be consumed by a single round trip. A crewed mission to Mars would use up most or all of an astronaut's allowable lifetime radiation exposure in one trip. That's before you consider the 2 years they'd spend on the Martian surface, which has no global magnetic field, only a thin atmosphere providing minimal shielding, and a sky that offers essentially no protection from cosmic radiation. The health consequences aren't just statistical cancer risk. Studies on rodents exposed to the kind of radiation spectrum found in deep space have shown alarming results. Cognitive impairment, memory degradation, changes in behavior, inflammation of neural tissue. There's growing evidence that long-duration deep space radiation exposure doesn't just increase cancer risk over decades. It may impair the mental function of the astronauts during the mission itself, which is a nightmare scenario for a mission that requires clear thinking and quick decisions in emergencies. Heavy shielding helps, but doesn't solve the problem. To bring deep space radiation exposure down to ISS levels, you'd need shielding equivalent to several meters of water surrounding the entire crew habitat. The mass of that shielding on a spacecraft designed to reach Mars quickly would be prohibitive. Compact nuclear shielding using polyethylene, water walls, or other hydrogen-rich materials can reduce exposure but not eliminate it. And galactic cosmic rays, which are not particles from the sun but high-energy atomic nuclei accelerated by supernovas across the galaxy, are so energetic that they pass through most practical shielding with ease. They interact differently with dense materials, sometimes making the problem worse by producing secondary radiation showers when they hit thick walls. There is no perfect solution. There is only mitigation and acceptance of risk. Now take the radiation problem and scale it to Jupiter. A crewed mission to Jupiter's moons would take years each way with any technology we're seriously discussing today. The radiation exposure would be multiple times worse than for Mars, and Jupiter itself generates powerful radiation belts that make its immediate vicinity lethally hostile to both humans and electronics. The Galileo spacecraft, which orbited Jupiter for 8 years, was deliberately crashed into Jupiter at the end of its mission, partly because the radiation had so degraded its systems. A crewed spacecraft in Jupiter's vicinity would face radiation levels that could incapacitate the crew in days. The outer solar system doesn't just challenge our propulsion. It's actively hostile to biology in ways that create hard physical limits. Barrier 3 is time and biology, and these are related in ways that most people don't fully appreciate. The human body was designed by evolution for one environment: Earth's surface, one gravity, one atmospheric composition, one magnetic field. Take it out of that environment, and it begins to fail. Not immediately, not dramatically in most cases, but steadily, measurably, progressively. In microgravity, bone density decreases at about 1 to 2% per month. Muscle mass atrophies. The cardiovascular system weakens because it no longer needs to fight gravity to pump blood upward to the brain. Fluid shifts toward the head, changing intracranial pressure in ways that may damage vision permanently. Some astronauts who spent 6 months on the ISS returned with measurably impaired eyesight, a condition now called spaceflight-associated neuro-ocular syndrome that we still don't fully understand or reliably prevent. The immune system weakens, the microbiome changes. Viruses that live dormantly in the body reactivate. Astronauts exercise 2.5 hours a day on the ISS specifically to fight these effects. And even with that extraordinary effort, they return to Earth after 6 months, needing weeks of rehabilitation to walk normally, rebuild bone density, and readapt to gravity. The record for continuous time in space is held by Russian cosmonaut Oleg Kononenko, who surpassed 878 days in space across multiple missions and spent 374 consecutive days on the ISS in a single stint in 2023 to 2024. That research has been invaluable, and it has confirmed that the human body can adapt to microgravity with effort, but it cannot thrive in it indefinitely. The degradation is real and it compounds. For a Mars mission, the journey in each direction takes 6 to 9 months in microgravity. Then there are 2 years on the Martian surface in 38% of Earth's gravity, which we genuinely don't know is enough to prevent bone and muscle loss. We have data from microgravity and from full Earth gravity. We have no data on humans living in partial gravity for extended periods because no one has ever done it. 38% gravity might be enough. It might not be. The first Mars crew is going to find out the hard way, and the return journey, another 6 to 9 months of microgravity, following 2 years in partial gravity, following 6 to 9 months of initial microgravity. By the time a Mars crew returns to Earth, their bodies will have been outside of full Earth gravity for between 3 and 4 years. We don't know what that does to human physiology at that scale. Some researchers have speculated, based on current trends, that the returning astronauts might be physically incapable of walking off the spacecraft upon return, that their cardiovascular systems, so thoroughly adapted to low-gravity environments, might fail under the sudden demand of a full 1G environment. This isn't pessimism. This is the extrapolation of data we already have. And the extrapolation gets worse the farther out you go. A mission to Jupiter's moon Europa, our most scientifically tantalizing destination in the outer solar system because of its suspected subsurface ocean, would take somewhere between 2 and 6 years each way. With any propulsion system we can realistically envision building in the next few decades, the total mission duration could be a decade or more. We're now talking about a human body subjected to microgravity or partial gravity for a decade. Radiation doses that exceed any established safety guidelines. Psychological isolation so profound that it would constitute a medical crisis by any Earth-based definition. And food production, water recycling, and life support systems that have to function perfectly for years with no possibility of resupply. We cannot currently do this. We don't have the biology to survive it. We don't have the psychology to tolerate it. We don't have the engineering to guarantee it. And the gap between where we are and where we would need to be to do this safely is not measured in years. It is measured in generations of research and development. Barrier 4 is communication, and this one is subtle, but it matters enormously. In space, all communication travels at light speed. For missions in the inner solar system, this delay is annoying but manageable. Communication with the ISS is essentially instantaneous. Communication with Mars at average distance takes about 7 minutes each way. If something goes wrong on Mars, you transmit a distress message, and 7 minutes later it arrives at Earth, where engineers look at the data, discuss it, formulate a response, and transmit back. 7 minutes later the crew receives it. A full exchange of critical information takes 14 minutes minimum. If the crisis requires multiple rounds of communication, you might wait an hour for what amounts to a single conversation. Medical emergencies on Mars don't wait for 14-minute round-trip communication delays. The crew has to be self-sufficient in ways that current mission architectures don't fully address. But for missions to the outer solar system, the communication problem gets genuinely severe. At Jupiter's average distance, a signal takes about 43 minutes each way. A round-trip message exchange takes nearly an hour and a half. At Saturn's average distance, roughly 80 minutes each way. At Neptune, over 4 hours each way. If you're trying to handle a medical emergency, a navigation crisis, or a life support failure at Neptune, and your fastest possible communication with Earth takes over 4 hours in each direction, you are functionally alone. Mission control might as well not exist. The crew has to have complete knowledge, complete capability, and complete decision-making authority for every situation that could possibly arise. That's an extraordinarily high bar that our current astronaut training programs aren't designed to meet at that level. This is one of the reasons Mars missions are so challenging, even though Mars is relatively close. It's not just the distance in miles, it's the communication latency, it's the isolation, it's the psychological weight of knowing that help, in any meaningful sense, is not coming. Every system that fails must be repaired by the crew with what they have on hand. Every medical crisis must be managed by the crew's medical officer, who is a trained physician but not a hospital. You cannot call Earth for real-time guidance when the answer takes 14 minutes to arrive. You handle it or you don't. Now let's add these barriers together and ask the question in a more structured way. Not just where can we go, but where is the realistic boundary, the point at which space actually wins. Let's build this up systematically. Low Earth orbit, up to about 1,200 miles altitude, is achievable right now, and we know how to operate there. The ISS demonstrates this. Crewed space stations are within our technical envelope. Though the radiation environment, even in low Earth orbit, is elevated enough to impose career dose limits on professional astronauts, the Moon is achievable. We've done it. The Artemis program, NASA's current mission to return humans to the lunar surface, is working toward putting the first woman and the next man on the Moon within the next few years. Lunar presence is within our near-term capability, though establishing a permanent outpost requires solving serious challenges around radiation exposure, micrometeorite impacts, lunar dust, and long-term life support. The Moon is not trivially easy, but it's doable. It's our nearest neighbor and we have decades of design work and to Apollo era mission successes worth of data to build on. Mars. This is the big one. The destination that dominates current planning from NASA, SpaceX, and space agencies around the world. Mars is achievable. The physics allows it. Chemical propulsion with nuclear augmentation can get humans there. The mission would be dangerous, expensive, and brutal on human biology. The radiation exposure would be severe. The communication delays would require extreme crew autonomy. The medical risks would be significant. But Mars is within the range of what humanity can, in principle, do if we commit the resources and accept the risks. SpaceX has publicly stated ambitions for crewed Mars missions in the late 2020s, and while those timelines have historically been optimistic, a human Mars mission within the next decade or two is not physically impossible. What comes after Mars is where the picture changes sharply. The asteroid belt, between Mars and Jupiter. This is a region populated by millions of rocky objects ranging from dust to the dwarf planet Ceres, which is about 590 miles in diameter. Crewed missions to near-Earth asteroids are theoretically feasible. NASA seriously studied a mission to redirect a small asteroid to lunar orbit and then visit it with astronauts. That concept was eventually abandoned, but the trajectory math works. Large asteroids in the main belt, though, would require journeys of 1 to 3 years each way. That's much more challenging biologically and logistically, but it's not impossible if you have the right propulsion and life support systems. The Jupiter system is where things get genuinely difficult. Jupiter is a minimum of 365 million miles from Earth and up to 600 million miles at maximum distance. A trip there with chemical propulsion would take 2 to 3 years each way. With nuclear thermal propulsion, which could become technically feasible in the next 20 to 30 years, transit times could be reduced substantially, perhaps to 18 months each way with aggressive mission architecture. But the radiation environment in Jupiter's vicinity is lethal. The mission would need to be planned carefully to minimize time near the planet itself, using the moons as temporary shields. The psychological and biological strain of a 4 to 6 year total mission would be extraordinary. The crew size required for redundancy and safety would be large. The spacecraft would be enormous by any current standard. Is it possible? In theory, yes. Would it require technologies we don't yet have? Yes. Are there meaningful scientific and possibly commercial reasons to go? Absolutely, particularly for Europa. But a crewed mission to Jupiter is not a near-term aspiration. It's a mid-21st century project at the most optimistic estimate. More realistically, a late 21st century project. Saturn and beyond. Saturn is between 746 million miles and about 1 billion miles from Earth. Uranus and Neptune are farther still. Crewed missions to these destinations, using anything resembling current or near-term technology, would take decades each way. These are not round trips in any individual human lifetime with conventional propulsion. The only realistic way humans reach the outer solar system in meaningful timeframes, by which I mean 5 to 10 years of transit, is with propulsion technology that doesn't exist yet. Not just incremental improvements, fundamental breakthroughs. Nuclear pulse propulsion, which involves detonating nuclear bombs behind a spacecraft to generate thrust, could theoretically reach Saturn in a few years. It's technically feasible based on physics worked out in the Project Orion studies of the 1950s and 60s. It's politically and practically impossible under current international law. And even if it worked, the radiation exposure from the nuclear detonations themselves would be a serious complication. Fusion propulsion, the holy grail that could make the outer solar system reachable, requires first solving controlled fusion, which we've been working on for 70 years, and which finally achieved net energy gain in laboratory conditions at the National Ignition Facility in December 2022. That's a real and meaningful breakthrough. But the distance from a laboratory result to a compact, reliable, spacecraft-mounted fusion drive is enormous. We're talking decades, minimum, quite possibly half a century. So here's where we land with our solar system survey. Near-Earth orbit and the Moon, achievable now. Mars, achievable within a generation with current trajectory of development. Asteroid belt, achievable with near-future propulsion. Jupiter system, achievable with mid-future propulsion breakthroughs. Outer solar system with human crews, requires fundamental technology we don't have yet, and may not have for a century or more. But all of this, everything we've discussed so far, is still inside our solar system. And the solar system, as vast as it is by human standards, is a tiny bubble in the ocean of space. The moment you step outside it, into interstellar space, the barriers don't just grow, they become categorically different in kind. Let's talk about the Oort Cloud. This is the theoretical outer boundary of our solar system, a vast spherical shell of icy bodies orbiting the Sun at distances ranging from roughly 2,000 to 100,000 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. The outer edge of the Oort Cloud is somewhere around 1 to 2 light-years from the Sun. A light-year is about 5.9 trillion miles, so the Oort Cloud, the outer edge of our own solar system, is roughly 6 to 12 trillion miles away. Voyager 1, our fastest and most distant probe, is currently about 160 astronomical units from the Sun. It would take approximately 300 years to reach the inner edge of the Oort Cloud, and another 30,000 years to pass through it. 30,000 years. That's longer than the entire span of recorded human civilization. And the Oort Cloud is still part of our solar system. It's still gravitationally bound to our Sun. The nearest star system, Alpha Centauri, is about 4.24 light-years away. That's approximately 25 trillion miles. At Voyager's speed, the journey would take about 75,000 years. The Apollo 10 crew set the human speed record at 24,791 miles per hour. At that speed, reaching Alpha Centauri would take about 115,000 years. The Roman Empire fell about 1,550 years ago. Humanity's entire written history spans about 5,000 years. Even the most optimistic interpretation of our species' duration on Earth covers maybe 300,000 years. And we're talking about journey times that are comparable to our entire evolutionary history as a species. This is what it means when people say interstellar travel is impossibly hard. It's not that the distances are large in an abstract sense. It's that they are large relative to human timescales in a way that seems physically meaningful. You cannot simply wait it out. No one lives 75,000 years. No government maintains funding or coherent goals for 75,000 years. No spacecraft maintains function without maintenance for 75,000 years. The problem isn't just engineering. It's fundamental mismatch between the scale of the universe and the duration of biological life. Now, you could imagine several approaches to this problem. Generation ships, where multiple generations of humans live their entire lives aboard a vessel during the interstellar journey. Suspended animation or some form of hibernation technology that puts the crew in a metabolic hold for the journey. Unmanned probes that relay back information and eventually seed a destination with technology to prepare for later arrivals. Or propulsion so fast that it compresses the journey into a human lifetime. Let's examine each. Generation ships are theoretically possible in the sense that humans can physically live on spacecraft. But a vessel capable of sustaining a minimum viable human population, which genetic analyses suggest requires at least a few hundred individuals to prevent genetic bottleneck effects, for 75,000 years or more, is an engineering challenge that dwarfs anything humanity has ever attempted by orders of magnitude. You need a completely closed-loop ecosystem that recycles all matter perfectly. You need a power source that operates for tens of thousands of years. You need a political and social structure that maintains its coherence and its mission focus across thousands of generations. You need to somehow prevent the inevitable genetic drift, cultural drift, and loss of technical knowledge that occurs over such timescales. The people who arrive would be so remote from the people who departed, biologically, culturally, and intellectually, that they might not recognize what they were part of. The mission might have been forgotten, mythologized, or actively abandoned centuries before arrival. Suspended animation or hibernation is an idea we don't currently know how to implement for humans. We can cool animals into torpor in laboratory settings. Some species do this naturally. The biological mechanisms exist in nature. But for humans, achieving safe extended hibernation where the brain and body remain viable for decades, let alone centuries, remains speculative technology. It might be possible. There's active research on the topic, but we don't have it, and we have no guarantee we'll develop it. Unmanned probes traveling at the speeds we can realistically achieve would take tens of thousands of years to reach even Alpha Centauri, which somewhat defeats the purpose of sending them to gather useful information in any human-relevant time frame. The Breakthrough Starshot Initiative has proposed using laser-powered light sails to accelerate gram-scale probes to 20% of light speed, which would get them to Alpha Centauri in about 20 years. This is genuinely interesting, and the physics works. But even if it succeeds, those probes would be tiny, capable of nothing more than flying past the target system at enormous speed and transmitting a few images and sensor readings before disappearing into the dark. They couldn't land. They couldn't slow down. They couldn't establish contact in any meaningful sense. And we'd wait for years for the data to come back at light speed. And then there's propulsion sufficient to compress the journey. Here is where physics imposes the hardest limit of all. To get to Alpha Centauri in a human lifetime, a spacecraft would need to travel at a significant fraction of light speed. At 10% of light speed, the journey takes 42 years. At 50% of light speed, about 9 years. At 90% of light speed, about 5 years. These are travel times that could, in principle, fit within a human lifetime, though barely. But the energy required to accelerate a crewed spacecraft to these velocities is astronomical. The Tsiolkovsky rocket equation applies here with brutal force. To accelerate even a small payload, say a few tons, to 10% of light speed, and then decelerate it at the destination, and then re-accelerate for the return, and decelerate again at Earth, requires fuel mass many orders of magnitude greater than the payload. With chemical propulsion, the fuel requirement is literally greater than the mass of the observable universe. That's not hyperbole. The math works out that way. You'd need more fuel than exists. With antimatter propulsion, which is theoretically the most efficient fuel source possible, converting matter directly to energy at 100% efficiency, the numbers become physically achievable, but practically impossible. Producing 1 gram of antimatter with current particle accelerator technology would cost roughly $100 trillion and take longer than the age of the universe to accumulate in useful quantities. The entire world's annual energy production could be converted to antimatter, and it would still only be enough to push a spacecraft to a tiny fraction of light speed. Fusion drives, the most plausible serious option, could theoretically push a spacecraft to perhaps 10 to 20% of light speed if the reactor is efficient enough and the mission is designed carefully. A fusion drive with exhaust velocities comparable to what fusion physics permits would be an extraordinary engineering achievement, requiring decades to develop, but it's not fundamentally impossible. 10 to 20% of light speed gets you to Alpha Centauri in 21 to 42 years, possible in a human lifetime. But the spacecraft would have to be massive. The crew would need to survive decades of deep space radiation, and decelerating at the destination requires as much fuel as accelerating, which means you're looking at fuel-to-payload ratios that make even this scenario almost inconceivably difficult. At higher velocities, relativistic effects start to help in one sense. Time dilation means that the crew ages more slowly than the universe outside. At 90% of light speed, the crew ages at about 44% the normal rate. At 99%, about 14% of the normal rate. This means a subjectively short journey from the crew's perspective, while decades or centuries pass outside. But this creates its own profound problem. You arrive at your destination, and everyone who sent you is long dead. You return to Earth and find it centuries different from the one you left. The civilization that funded and launched you may not even exist anymore. and the energy required to reach 99% of light speed is essentially infinite for any massive object. Special relativity imposes this as an inviolable law. As you approach light speed, the energy required to accelerate further increases without limit. You can get to 90%, you can push to 99% with enough fuel, but the fuel requirement grows exponentially, and without a physical bound, you never quite reach light speed. And without reaching light speed, you never quite collapse the journey to zero time. This is what space winning looks like in the interstellar domain. The distances are measured in light years. The journey times at realistic speeds are measured in human generations. The energy requirements are measured in quantities that dwarf our civilization's total output. And physics imposes these as fundamental constraints, not engineering problems to be solved with cleverness. They are features of how reality works. But there's one more dimension to this problem that most discussions miss, and it may be the most sobering of all. The expanding universe. Space is not static. The universe is expanding, and that expansion is accelerating. Every galaxy beyond our local group is moving away from us, and the farther away it is, the faster it recedes. This is not because galaxies are moving through space at high speed, it's because space itself is expanding. The fabric of the universe is stretching, and it carries everything with it. At the current expansion rate, described by the Hubble constant, galaxies at a distance of about 14 billion light-years are receding from us at the speed of light. Beyond that distance, they're receding faster than light. Their light will never reach us, not because they're moving through space faster than light, but because the space between us is expanding faster than light can traverse it. These galaxies have crossed our cosmological horizon. We can't see them, we can't communicate with them, we can't reach them, ever, with any technology physically possible. Right now, the observable universe extends about 46.5 billion light-years in any direction, a sphere roughly 93 billion light-years in diameter. This is the extent of everything we can possibly observe, bounded by the cosmic horizon. But here's the terrifying part. The accelerating expansion means that this horizon is not fixed, it's shrinking. Not in absolute terms today, but more and more galaxies are crossing the horizon as expansion accelerates. Galaxies we can see today are already receding faster than light, meaning the light we're receiving left those galaxies long ago when they were closer. The light leaving those galaxies now will never reach us. They've already vanished from our reachable future, even though they haven't yet vanished from our observable present. Give this process enough time, a few trillion years, and the only galaxy visible in the sky from Earth will be our own merged Milky Way and Andromeda system, which are gravitationally bound and will merge in about 4 billion years. Everything else will have been carried beyond the horizon by accelerating expansion. Future civilizations, if any exist, will look out at a completely dark sky except for their own galaxy. They won't be able to detect the cosmic microwave background. They won't be able to measure the expansion of the universe. They won't even know the universe had a beginning. All the evidence will have been carried away by expansion. We are fortunate to live now, in an era when the evidence is still visible. For the question of how far humanity can travel, the expanding universe adds a cosmic cutoff that goes beyond propulsion and biology. Even if we somehow solved every engineering problem, even if we built ships that could travel at arbitrary fractions of light speed, the volume of the universe physically accessible to us is finite and is shrinking over cosmic time. There is a sphere around us, roughly 16 to 18 billion light-years in radius, that represents the maximum extent of what we can ever reach, even in principle, even with infinitely advanced technology. Beyond that, the expansion of space is permanently outrunning even light. We can never get there. Not in a million years, not in a billion years, not ever. The universe has drawn a circle around us and it's shrinking. This is the ultimate answer to the question, how far can humanity actually travel before space wins? Space wins, definitively and irrevocably, at roughly 16 to 18 billion light-years in every direction. That's the hard limit imposed by the geometry of an accelerating, expanding universe. Beyond that, nothing we ever build or conceive will ever go. But that ultimate cosmological limit, while philosophically important, is so far beyond any practical human concern that it almost doesn't matter for the near and medium term. The limits that actually matter, the ones that affect real decisions being made by real people right now, are much more proximate. Let's be honest about the practical envelope. Where can we actually go within the next 100 years, given a realistic but aggressive level of technological development? With the technologies we are currently developing, or could realistically develop in the next few decades, humans will probably reach the moon again in the next few years and establish some kind of permanent or semi-permanent presence there within the next decade or two. Humans will reach Mars, almost certainly, within the first half of this century. Whether that's 2030s, 2040s, or 2050s, depends on political will, funding, and whether the first few attempts reveal fatal problems we haven't anticipated. But Mars is coming. A crewed mission to a near-Earth asteroid will happen within this century, probably within the next 30 to 40 years. A crewed flyby or orbital mission to Venus is possible within a similar time frame, though the surface of Venus is so hostile that landing there is beyond any near-term capability. Crewed missions to the Jupiter system, specifically to orbit or visit its moons, would require propulsion systems we don't have yet, but might develop by mid to late century if fusion or advanced nuclear thermal propulsion becomes practical. This is not guaranteed, but it's within the range of physical possibility. Beyond Jupiter, in the next 100 years, probably not with human crews. The outer solar system and beyond represents an escalating series of challenges that current development trajectories don't reach within that time frame. In the next 200 to 500 years, assuming our civilization survives and continues technological development, the realistic outer limit of human presence might extend to Saturn's moons, perhaps Titan with its thick atmosphere and exotic chemistry, and possibly the ice moons of the outer solar system if we solve the radiation and propulsion challenges. But even this is optimistic. The biological challenges alone, the fundamental mismatch between human physiology and the space environment, might require biological modification, cybernetic augmentation, or the development of genuinely post-biological humans who can tolerate conditions that pure biology cannot. And for interstellar travel, the honest answer is this: not within any human civilization's near-term planning horizon, not in the next century, not likely in the next millennium with purely incremental progress. Reaching another star system in a meaningful way, with crews who can establish a presence and return, requires either propulsion physics we don't currently understand, or timescales so long that the civilization launching the mission will not recognize the civilization receiving the results. This is not despair, this is physics. And physics, when you stop fighting it and start understanding it, gives you something more valuable than hope. It gives you a realistic map. Now let's talk about the question that makes this relevant to your life, and not just to hypothetical future generations. What does this mean for how we think about our place in the cosmos? What does it mean for the search for extraterrestrial intelligence? And what does it mean for the long-term survival of our species? The travel limits we've described explain something important about the Fermi paradox, the puzzling observation that if intelligent life is common in the universe, we should see evidence of it everywhere, and yet we detect nothing. One natural response to the travel limits we've described is that maybe everyone faces the same limits. Maybe every intelligent species that arises in the galaxy runs into the same walls. They can colonize their own planet. They can perhaps reach a few neighboring stars after centuries of effort. But spreading across a galaxy is extraordinarily difficult even for the most advanced civilization, and the galaxy is 100,000 light-years across. The timescales are vast, the engineering requirements are enormous. The galaxy might be full of isolated civilizations, each separated by hundreds or thousands of light-years, each unable to communicate or travel between each other in any time frame shorter than geological epochs. The silence of the universe might not be the silence of emptiness, it might be the silence of separation. Everyone locked in their own bubble by the same physics that locks us in ours. For the survival of our species, the travel limits are directly relevant. One of the strongest arguments for space colonization is that it makes humanity multiplanetary, reducing the risk that a single catastrophic event, an asteroid impact, a pandemic, a geomagnetic reversal, a nuclear war, could end our entire species. Putting humans on Mars accomplishes this. If Earth is catastrophically damaged, the Martian colony survives. Humanity continues. This argument for Mars is real and important, and it works within the travel envelope we've described. Mars is reachable. A self-sustaining colony there is physically possible, even if extraordinarily difficult. But the argument for colonizing Alpha Centauri as a backup for Earth doesn't work on timescales relevant to the threats we face. Interstellar travel takes generations with any technology we can realistically envision. The threats to Earth that we worry about most are threats that could materialize within decades or centuries, not millennia. A colony ship can't launch fast enough to serve as a meaningful hedge against threats that play out on human timescales. The existential backup must be within the solar system, Mars, and eventually perhaps some of the moons of the outer planets, if we extend our timescale to centuries. There's also the question of what the limits mean for our conception of ourselves. Humans have spent thousands of years imagining that the stars are destinations. We named them, told stories about them, pointed at them and wondered. We've built civilizations around the idea that we are explorers, that the frontier is always beyond the next ridge, the next ocean, the next atmospheric boundary. Space colonization has inherited this narrative. The stars are out there, and someday we'll go. But what the physics actually tells us is more nuanced and more interesting than either pure pessimism or pure optimism. The stars are out there. Some of them might be reachable in principle, with the right technology and the right scale of commitment over the right time scales. Our immediate neighborhood in space, the Moon, Mars, the asteroid belt, possibly the inner moon systems of the outer planets, is reachable within a human civilization's planning horizon. These are not trivial destinations. They represent worlds that humanity has never set foot on, environments that might reshape what it means to be human, resources and perspectives that could transform civilization. And beyond our immediate neighborhood, there is a boundary, not an absolute barrier, but a sliding scale where the requirements escalate faster than the benefits accumulate. The outer solar system is extraordinarily difficult. Interstellar space is essentially beyond us with current physics. The cosmological horizon is absolutely beyond us forever. But here's something worth sitting with. The fact that there are limits is not a failure of imagination. It's evidence that we exist inside a real universe with real rules. The rules are not malicious. They're not designed to frustrate us. They're just the way space, time, energy, and matter actually work. And understanding the rules, knowing where the walls are, is the only way to make genuine progress. We spent centuries believing the Earth was the center of the universe. Then we learned it wasn't. We spent centuries believing our galaxy was the whole universe. Then we learned it wasn't. We've progressively discovered that our place is smaller and more humble than we imagined at every scale, while simultaneously discovering that the universe itself is larger and stranger and more magnificent than we imagined. Understanding our limits has always been the first step toward genuinely pushing them. The moon's gravity is a limit. We built rockets and went anyway. The vacuum of space is a limit. We built pressure suits and went anyway. The radiation of low Earth orbit is a limit. We designed medical protocols and went anyway, accepting elevated risk for the rewards of discovery. The distance to Mars is a limit. We are building the spacecraft and going anyway, accepting the biological challenges, the communication delays, the long-duration isolation, because what we might find and what we might learn and what we might become as a species on a second world is worth the cost. And so perhaps the right framing is not how far can humanity travel before space wins. The right framing is where is the next frontier that we can reach with sufficient effort, and what will it take to get there? On that framing, the moon is the immediate frontier. Mars is the grand challenge of our century. The asteroid belt and inner Jupiter system are the aspirations of the generation after ours, and the outer solar system and beyond are challenges for civilizations we haven't yet become. Space doesn't win at some fixed distance. Space applies escalating penalties for increasing ambition. The question is what penalties you're willing to accept in exchange for what rewards. And the answer to that question is not written in physics. It's written in human choice. Let's be specific about what the next 10 to 20 years actually look like. Because the gap between current capability and future vision is worth examining honestly, without either breathless optimism or dismissive cynicism. The Artemis program is NASA's effort to return humans to the moon and establish a sustained lunar presence. Artemis has had delays. The first crewed Artemis flight around the moon slipped from earlier planned dates, and the first crewed lunar landing has been pushed back multiple times. But the hardware is real. The Space Launch System rocket has flown. The Orion spacecraft is tested and qualified for crewed flight. Commercial lunar landers from companies like SpaceX, using Starship, are in development. A lunar gateway, a small space station in lunar orbit, is being planned as a staging point. The architecture exists. The timeline keeps slipping, but the direction is clear. SpaceX's Starship system, which completed several full integrated test flights in 2023 and 2024 and achieved important milestones, including controlled ocean, splashdown of the Super Heavy booster and the ship vehicle represents a potential revolution in launch economics. If Starship achieves its design goals of full reusability and high launch cadence, the cost per kilogram to orbit drops by perhaps an order of magnitude compared to current options. This changes the calculus significantly, not just for Mars, but for everything in between. Cheaper access to space means more missions, more hardware deployed, more crew time in space, more data about long-duration human space. China has an ambitious lunar program with stated goals of crewed moon missions and eventually a moon base. Several other countries, including India, Japan, and the European Union, have expanding space programs with increasing capabilities. The international landscape of space exploration is more competitive and more active than at any point since the Apollo era. On the propulsion front, NASA and DARPA are both funding work on nuclear thermal propulsion, which could reduce Mars transit times to as little as 3 to 4 months with the right reactor design. This matters enormously for crew health. Every month in deep space is a month of radiation exposure. Every month of reduced transit is a month less bone loss. Cutting the transit time to Mars in half significantly improves the biological outlook for the crew. Private companies are actively developing technologies relevant to deep space habitation. Axiom Space is planning a commercial space station. Several companies are developing life support systems optimized for long-duration spaceflight. The NASA Artemis program is explicitly designed as a proving ground for technologies and systems that will be needed for Mars. Every challenge we solve on the Moon or in lunar orbit moves the Mars capability forward. On the biological side, research continues on countermeasures for microgravity effects. Pharmaceutical approaches to bone density loss are being studied. Exercise protocols are being refined. Radiation shielding concepts using hydrogen-rich materials are being tested. We won't have perfect solutions by the time the first Mars crew departs, but we'll have significantly better ones than we have today. The unmanned robotic program is remarkably healthy. The Perseverance rover is sampling Martian rocks for eventual return to Earth, which will tell us whether Mars ever harbored microbial life. The Ingenuity helicopter, a technology demonstration that was supposed to fly 5 times, has flown more than 70 times before its mission ended in January 2024 when it damaged a rotor blade, demonstrating that aerial exploration of Mars is feasible. The Europa Clipper mission, launched in October 2024, is on its way to Jupiter's moon Europa and will conduct close flybys starting in 2030, characterizing the ice shell and the subsurface ocean and determining whether the conditions for life exist there. This is one of the most scientifically exciting missions in human history. The James Webb Space Telescope, now fully operational after its launch in December 2021, is transforming our understanding of the early universe, exoplanets, and the conditions for life throughout the cosmos. Its infrared sensitivity allows it to study the atmospheres of exoplanets in the habitable zones of nearby stars, searching for biosignatures that might indicate life. Webb is not a travel technology, but it's expanding the map we're trying to travel. All of this represents momentum, real, measurable momentum. The question of how far humanity can travel is not static. The envelope is expanding, slowly in some areas and more rapidly in others. The limits I've described are real, but they're not all immovable in the same time frame. Some are engineering problems with plausible solutions. Others are physics problems with no currently known solutions. And understanding which is which matters. So let's come back to the central question one more time. With all of this in mind, how far can humanity actually travel before space wins? In the next century, the realistic answer is the inner solar system, the Moon, Mars, possibly the near-Earth asteroids and the inner asteroid belt. With aggressive development, the Jupiter system might be reachable by crewed missions in the second half of the century. But this requires propulsion breakthroughs we don't currently have. In the next millennium, with centuries of accumulated technological development, the outer solar system becomes plausible. Saturns, moons, Uranus, Neptune. But interstellar travel remains essentially impossible without physics we don't understand. In the next 10,000 years, the nature of humanity may have changed so fundamentally through biological modification, artificial intelligence, or technologies we can't conceive today, that the limits I've described become irrelevant in ways I can't predict. The entity that might reach another star 1,000 years from now may not be recognizably human. It might be post-biological, it might be artificial, It might be something that hasn't been named yet. And beyond 10,000 years, the universe continues expanding. The cosmological horizon continues closing, and the long-term future of intelligence in the cosmos, whether it's human or something descended from humanity or something completely unrelated to us, faces the same fundamental constraints. A universe with a finite accessible volume that is slowly shrinking, in which complexity and life are rare and temporary, and in which the laws of thermodynamics ensure that everything ultimately trends toward cold equilibrium. Space wins in the very long run. The second law of thermodynamics guarantees it. The heat death of the universe, that final state of maximum entropy from which no useful work can be extracted, is the universe's ultimate victory. But that's 10 to the 100 years from now, a number so vast it makes the age of the universe look like an eye blink. Between now and then, there's an enormous amount of universe to explore, a finite but extraordinary volume of space that contains billions of stars and possibly billions of inhabited worlds, and enough time for biology and intelligence and curiosity to do remarkable things. The limit is real. Space wins eventually, but not today, and not before we've had a chance to find out what the universe actually contains. There's a perspective that helps me sit with all of this without despair. Every generation of humans has lived inside a bubble. For most of human history, that bubble was a village. Your world was the valley or the plain or the forest you were born in, and the neighboring settlements you might visit in a lifetime. Then boats expanded the bubble to include continents. Then airplanes collapsed the planet into a single connected world. Then rockets punched a hole in the atmosphere and we looked down at Earth from outside for the first time, and something changed in how we understood ourselves. We are right now, in April of 2026, at the very beginning of the next expansion. The moon is being treated as a destination again, not just a memory of what we did once and then abandoned. Mars is being planned for in earnest, with spacecraft being built and tested right now. The solar system is opening up, slowly, painfully, with enormous difficulty, but genuinely opening. The walls we've described are real, but they're walls we're pushing against. And the history of our species suggests that walls we push against long enough eventually develop doors. The distance to the moon seemed impossible in 1900. The idea of people living in space for months was science fiction in 1950. The concept of a Mars colony was a fantasy in 1970. None of that has changed the underlying physics. Light still travels at 186,000 miles per second. The rocket equation still applies. Radiation still damages DNA. Biology still requires certain conditions to function. But we have found ways, imperfect and difficult and costly ways, to operate within and around those constraints. We built life support systems. We designed radiation shielding. We developed countermeasures for bone loss and muscle atrophy. We created communication protocols that work across interplanetary distances. We haven't beaten the physics. We've learned to live inside it. That's what humanity does. Not conquer nature, but negotiate with it. Find the terms on which the universe will allow us to exist in places evolution never prepared us for, and push those terms as far as physics permits. How far can humanity actually travel? Far enough to change everything we think we know about what it means to be human. Far enough to guarantee the survival of something that thinks and wonders and cares, even if the Earth is somehow lost. Far enough to answer questions about life in the universe that have haunted us since we first looked up at the stars and asked whether we were alone. Not to the cosmological horizon, not to the nearest star in any near-term planning horizon, not without extraordinary difficulty, risk, and cost at every step beyond the moon, but farther than we've been, always farther than we've been. And that, in a universe 13.8 billion years old, that gave us exactly this moment, and this window in which to look up and ask the question, is enough to keep going. The silence between stars is vast, the distances are humbling, the limits are real. But we are here right now, at the beginning of the expansion, pushing against the first walls. And what we do in the next 100 years will determine how much of the universe is remaining accessible. Volume humanity ever gets to see. That's not a small thing. That's everything. Thank you for spending this time with us on this journey through what physics actually allows and what it forever forbids. If this changed how you think